I have to find the area under the curve. Let's call it the curve given by the function f. Okay, so we don't know how to compute exactly the value of this area. We know under using simple shapes like rectangle, okay, or triangle. We know the formula for this. Okay, so for this one, you have height, length times height. Okay, so L times capital L. Here, if this is the height, and this is the basis, we call it basis, then the area will be half of the base times the height. Here the area, so this is capital L, this is L, size of the sides of the rectangle. Yes. So how will we will compute this? So the idea is to use simple shapes like the rectangle, the shape of rectangle. So how we do that? Here is how it works. We use a subdivision. So subdivide EB. The interval EB is sub-intervals. So we will use points x0. So let's say this one is x0. Then we will have x1, x2, etc. till we reach xn. So up to us to choose n large enough for. Okay, so here it is. So we have x0, we said a less than x1 less than x2 less than etc. Okay, so we have subintervals, so we form subintervals x0, x1, then x1, x2, etc. Let's say xi minus 1, xi up to xn minus 1 to xn. Okay, so then the idea of Riemann is to choose a particular point, a point inside in such subinterval. Okay, for a moment, let's take it arbitrarily. So let's say this is x0 star. Okay, x0 star, x1 star, or x1 star, x2 star, etc. Okay, so yes, and we have xi star chosen in the interval xi minus 1, xi. Okay, so then we assign to the xi this point value taken by f. So at this point it's f at xi star. And then the idea is to consider the rectangle with basis xi minus, okay, and height this one. So we form a rectangle, and the rectangle we can compute its area. Okay, so the area of this rectangle, we know its area. So the area equal, so f the height times xi minus 1. So suppose that we repeat this process. We repeat it. Here is xi star, the value taken by f. This is the height. Consider the corresponding rectangle with basis this one. Okay, another rectangle, etc. And we repeat again. Okay, for x2, let's say here it is. So I will have something like that and go down. Okay. Okay, and we form, and imagine that we repeat each time and we add these areas. So the total area of rectangles will be then So f x1 star x1 minus x0 plus f x2 star times x2 minus x1, etc. f xi star xi minus 1 up to f xn star and xn minus 1. Okay, this sum like that, we use the sigma notation and write it like that as f xi star xi minus 1 I from 1 to n. Okay, and this sum is an approximation. Of course, it's not the exact, it is an approximation of the exact area. Okay, but we want the exact area. So the exact area, intuitively, we can imagine increasing the number of points. So we will get thinner rectangles, and then and more rectangles, so that we will approach more accurately our exact area. So to express this idea, we will set the following definition. So here is the definition of the area under curve. The area under F, okay, will be, okay, so area under the graph of F over the interval EB is denoted first. We will denote it like that. We keep the information F as function of X, the interval EB. Okay, so is equal to this number. We will set it as the limit of this sum, limit of the sigma fxi star xi minus 1 I as n increases indefinitely. Okay, when the limit exists. When the limit exists, that means it is a finite number. So this is what we will call our area under the region F. Okay, and this sum is called Riemann sum. This sum is called Riemann sum. There is so the definition is related to a limit. There is a precise definition for this. Let's give it just to have an idea how does it work. So a definition, let's say precise definition for the limit, or just continue instead of doing like that, proceeding like that. So this limit exactly means, so we can write it here. We can say that EB fx dx equal a number, this limit, okay, if and only if for any epsilon positive we can find a delta positive, so that this number, okay, minus a Riemann sum, so okay, at n delta xi is less than epsilon for any partition P of EB, with the maximum of the size of the subdivision is less than delta for any xi. For it shouldn't depend on the choice of the point, intermediate point xi star. Okay, so this is what the theorem, the definition says. Okay, so this is what we set as definition. Okay, so yeah, we have some terminology. yes, so it's good to know. That is good to know. Here it is. So the note, so it's about notation here. So when we write a to b fx dx, so e is the left, a and b are limit of integration. E is the lower limit of integration. Uh, b is the upper limit of integration. F is the integrand function. What else? The integral sign for this. This is the symbol. This symbol is the integrand sign. And dx indicates. So dx just indicates the variable, the independent variable x. Okay, the variable x. Okay, that's all. So this is what you need to know. Okay, and so you see it indicates, and you can always have, and we have, it's just we can always, so the area doesn't depend on the name of x. We have a to b fx dx. We can change the name of variable because we are computing in area. So we can say ft dt equal fr dr, etc. It doesn't depend on x. It's a number. Okay, so it doesn't depend on x. Okay, it's a constant, it's an area. So this is what we set as definition. Okay, now let's do some examples. Let's compute some areas of functions, simple functions, of course. Let's start with simple functions. So okay, so this is the section is about definite integral. Okay, definite integrals that we call also area. Okay, so let's do an example here. So what if I have to compute the integral from e to b, first example, of a constant or 1, okay, 1 dx. Why not from 0 to 1? Let's do 0 to 1, okay? Let's do simplify our calculation and do just from 0 to 1 dx. Okay, so let's consider subdivision. So we have here, it is, we are expecting the answer if this is 0 1, and my function fx is, this is my function fx here is 1. Okay, so this is my fx is 1. So the graph, I know it's horizontal line. Okay, it's not well graphed here, so let's do it here. Here it is my function. Okay, so it is clear that the area I am expecting it's 1 times 1. I'm expecting the value 1. Okay, so let's show it using the Riemann sums and the limit, etc. So we need to subdivide our interval 0 1 into subintervals and subintervals. So we define x0 equals 0, x1 equal, so let's use a regular partition. Regular partition means that the delta, the xi minus 1, the length of the sub-intervals are the same. We denote it delta x, and it are obtained by, so b minus a divided by n. We have n subintervals, the total length divided by n. So here in our case it's 1 minus 0 over n, which is 1 over n. So I will have then x1. If this is x0, then x1 will be here. It will be from 0, I add delta x, the size delta x. Okay, each time I move by delta x until I reach this one. Okay, this is my xn. Okay, so will be 0 plus delta x, which is 1 over n. x2 will be x1 plus delta x. So 1 over n plus 1 over n will be 2 over n, etc. Okay, so so finally xn or xi will be I times delta x will be I over n. Okay, so my sum Riemann sum xi from 1 to n fxi. Okay, so here also, yes, I didn't say that, so we are choosing the endpoint, the right endpoints. So this is a right point rule, rule. So we will say it, yes. So it will be fx1 plus delta x plus etc. until fxn delta x. So it will be fx1 is 1 times 1 over n plus then 1, my function is constant, okay, delta x, then 1 over n, etc. Here it's 1 times 1 over n. So I will have n times 1 times 1 over n, which is 1. Okay, so my sum already is always equal 1, and taking the limit of constant function, constant sequence here, okay, it will be 1. That's why, we have justified the equality. Okay, so let's now do another example. So just yes, here is the second example. This time let's do something x dx. Okay, so it form quickly. So my xi will be the same as this one. Okay, so I will have sum fxi delta x from 1 to n. So it will be fxi, so it will be xi sum, so the limit, don't forget limit sum, fxi will be xi, delta x is 1 over n. Now xi, we said it's I delta x, so it limit I delta x. I delta x is 1 over n. So it will be, what did I do here? Yes, 1 over n and 1 over n. Okay, so we will have some limit. I forgot the sum. So I need to compute the limit. Okay, I need to compute then the limit of the following sum. So 1 over n square is a constant sum I from 1 to n goes to infinity. Okay, so I can put n outside the sum. Now look at, I need to know explicitly this quantity. So this quantity is not easy to find. We use recurrence deduction. By deduction we prove deduction reasoning, we prove the following. We prove that this sum is exactly has the formula n times, look, n times n plus 1 over 2. Okay, and which then I can compute the limit. Okay, so I can take n here as factor, so I will have n2 1 plus 1 over n and over 2, then simplify and then deduce the limit, it's 1 over 2. Okay, and we can check also here by using geometry, because my line, I know it here, y equal x is the line passing to the origin and the point 1 1, but here is my line. Okay, and I'm going up to, yes, the interval 0 1. So I have the square, the area of the total square is 1, and here I have just a half of the area, so I have exactly 1/2. Yes, it's the area is 1/2. This is what we found here using Riemann sums. But now the purpose of this introducing these examples is to show you how it is complicated to compute such sums. It's not easy each time. So using Riemann sums, it's not a practical way to find the area. So we need to establish, to find other ways, more practical ways. And this is the purpose of the coming sections, where we introduce algebraic methods, take into account sometimes geometry, develop other techniques of we call integrations. Okay, so that yes, we can have more, yes, we can be able to compute more areas.